Good afternoon, everyone. Thank you so much for joining my presentation. My name is Thang Bui. I am currently a PhD candidate from Electrical Engineering Department, New Jersey Institute of Technology. Today, I would like to talk about full color micro LEDs for display technology. Here is the outline of my talk. First, I would like to give you some background information. Then, what are the current challenges with micro LEDs? Next, I will be showing you how I approach to overcome such challenges with nano-wide LED for full colors. And then what result I get and followed by discussion. Finally, conclusion. Let's start with the evolution of full color display technology. The CRT is the first generation of kind of display. It came out in the middle of the 20th century, several decades before the LCD display were commercialized. After that, OLED was introduced in 2007. The latest generation of displays, which promisingly change the world of displays, is based on micro LEDs. It is not commercial yet. Here the question is, what does micro LED display look like? Let's take an example. Imagine an Apple Watch with the view of micro LED display. When we look closely to these color rings, they are actually an array of micro LED emitting red, green, and blue color. As we well know that red, green, blue are primary color of light. Any other color is can some combination of these three. So yet, one pixel is a set of three red, green, blue micro LED, and the size of each micro LED in 100 micron or smaller. This kind of display offer better display quality, higher resolution, less power consumption. However, there are several current challenges of making full color micro LEDs. Here we can see a typical structure of thin film LED on the market. This consists of an active region in the middle of N-GaN layer at the bottom and the B-GaN layer on the top. When we look at closely at the active region, the in-GaN layer in the location somewhere in between two barrier L-GaN layers. However, this structure turned out some problem due to the difference in lattice constant and thermal coefficient between gallium nitride and silicon. The structure turned out very high threat in this location. Second, when we look at the active region, at the in-GaN L-GaN interface, the deformation happen. That's create high polarization. That create high polarization in the structure. Due to such drawback, this structure is limited to blue LEDs only, because in high indium composition for green and red LED, the structure doesn't work well. To overcome this challenges, we use nano-wide structure. Due to a small interfacial area to substrate, nano-wide can grow on silicon mismatch substrate with minimal threat in this location. And when high indium composition grow on gallium nitride, because of high elastic strain relaxation, the polarization at the interface between two materials can be reduced significantly compared to the thin film structure. And because of the nanostructure, the high surface to volume ratio of a nanowire have uh, have is have very high thermal dissipation. That's a very advantage compared to the thin film structure. Moreover, with a nanowire, beside the color changed by indium composition or gallium composition, the crystal dimension can be used to tune the color. For example, small diameter produce blue wavelength, but in the same indium composition, when nanowire have bigger, the wavelength we had, the color we had around in the yellow or red. Due to such advantage, we have designed LED structure with 10 quantum well. Each layer in this quantum well is around 3 nanometer, grow on silicon substrate. This nanowires grow by molecular beam epitaxy, and the SEM image show that the nanowires are relatively uniform across over the substrate, and their length is around 600 nanometer, with an average diameter in 80 micrometer. After fabrication process, we achieve an array of micro LEDs. And if we pick up an LED to see under optical microscope, we can see here the circle area in the emission. The circle is the emission area where the light comes out. The diameter of circle 50 micron is just a half compared to a typical micro LED. Electrode in its had the same size but is square, and injection current is delivered uniformly into the emission area by kind of threading layer. Individual micro LEDs micro LEDs are separated by the insulator. Let's move to see photoluminescent characteristic of red, green, blue micro LED. By changing indium composition from 21% to 32% to 43%, we have blue, green, and red micro LED. 475 nanometer for blue, 550 nanometer for green, and 645 nanometer for red, and spectral light width of BL emission around 50 nanometer. Let's move to see electroluminescence of red and green micro LED. Here we can see under different injection current from 50 milliampere to 350 milliampere, the red and green micro LED, the emission peak stay at the same value for red around 645 nanometer. For green micro LED, emission bit stay around 550 nanometer. The bit remain the same value, so that's why it's reduce the shifting effect. That's the shifting effect in present in thin film structure. Similarly, for blue LED, we can see here under different injection current from 50 milliampere to 350 milliampere, emission bit around 475 nanometer. When we draw emission bits as a function of injection current, we can see here the variation of red micro LEDs is around 1.5 nanometer, and for green and blue micro LEDs, variation peaks around 3 nanometer. So stability of this emission under injection current make this red, blue, and green micro LED very suitable for micro display application. In conclusion, high crystalline in-gain L-gain nanowire have been successfully grown with MBE technique. Full color red, green, blue micro LEDs in silicon have been made compatible with electronics industry. Such these micro LEDs are perfectly suitable for micro LED display application. And I would like to thank my group member, Professor Hugh, and thank you for all of you. Please have a question. Thank you.